this part, the 3/8 is a proper fraction. And a proper fraction just means that the numerator, this top number, is strictly less than the denominator, the bottom number. And so it has to be less than, as in it cannot be greater than or equal to. So this top number cannot be 8, and it can't be anything greater than 8, okay? So if the top number is less than the bottom number here, we have a proper fraction. So if I have a whole number and a proper fraction together, I have a mixed number. And when I talk about an improper fraction, that's just the opposite of this. I might have something like, let's say, 11/8. Okay, this is an improper fraction. Just being the opposite of a proper fraction, it just means that the numerator, the top number, is greater than or equal to the bottom number, the denominator. So 11 is greater than 8. So this is an improper fraction. But there's no whole number now here on the side, okay? So it's just a something over something, okay? So these are the two situations that we're working with today, that we're converting between. And it just so happens that the two examples that I used are equivalent. That's what we mean by converting. So if I say, how do I convert from a mixed number into an improper fraction, it means that I take this and I make it into this. These have the same values. I'm going to talk about how and why. But that's what we mean. We're just finding something equal to this, but in this particular form. And same vice versa. If I say, here's an improper fraction, convert it into a mixed number, it means I'm taking this and making it into this form with the whole number and a proper fraction instead of just this over this. Okay, so in both directions here. Okay, so for those of us who want to just know how to do it, the how-to, right? This is what was in my short flashcard. To go from a mixed number into an improper fraction, you take this denominator number, you multiply it by the whole number here, whatever's over here, and you add this. So 8 times 1 is 8. 8 plus 3 is 11, and that's how I get this 11. And then I put the whole thing over 8 anyway, so you just keep that denominator. So 8 times 1 plus 3, and we'll come back to this little pattern in a second, okay? But that's just kind of the shortcut thing. This times this plus this, and then all over this. What are we actually doing here? Well, the reason why we keep this 8 is because this denominator, this bottom number, essentially tells us how many pieces I want to break my quote-unquote my whole unit into. So 1/8 means that I take, let's say, a pizza. This whole thing represents 1. Okay, so 2 pizzas, 3 pizzas, 4 pizzas, whatever, right? But 1 pizza. This bottom number tells me how many equal pieces I should break this pizza into. So in this case, we have 8 represents 1/8. So how many 1/8 pieces, how many of these slices are in one pizza and 3/8? So we can draw out however many pizzas we want, right? They should all they should be the same, but we can cut them up into 8 pieces for this idea, right? No harm in just copying however many, but we are actually going to count the number of slices here. So in this case, for one whole pizza, how many of these 1/8 slices do we have? Well, for a whole pizza, we have 1, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8, right? 8 1/8 pieces make up the one whole. So this is my 1, and then it says that I have 3/8. So for the next part, I have 1/8, 2/8, and 3/8 of another pizza. So how many slices do we have in total? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 1/8 slices. So that's why we have 11/8. So essentially, this 1 is actually rewritten as 8/8. The denominator tells us how many slices to cut our 1 into. So this is basically, conceptually, 8/8 plus 3/8, which is 8 plus 3 is 11, and then the 8 still stays the same. You keep the denominator here. Essentially, this 1 is actually 8/8, and then we add our 3/8. So in total, we have 8 plus 3, which is 11/8 pieces, 1/8 pieces, right? So that's why the bottom number stays the same, because this determines basically the size of our slice, right? But how we divide up this 1, how many pieces we define 1 to be, basically. So that's why we don't do 8 plus 8, because the slices should be all the same here. It's not suddenly now splitting them in half into 16 pieces, right? We keep the same denominator. Now we have 8 plus 3, so we have 11/8 pieces. Okay, excellent. So now I'm going to change things up very slightly. Let's say instead of 1 and 3/8, I have 4 and 3/8. Okay, so we're going to follow our intuition here, what we were just building. And so again, our pizzas are divided into 8 equal slices. Okay, each pizza is going to be divided into 8 equal slices. Okay, so that each slice is 1/8. So now, if the question is, how many 1/8 slices are there in 4 and 3/8 pizzas? Here, I want to count the total number of slices. So, with my 4 whole pizzas, each pizza has 8 slices, right? So for 4 whole pizzas, I have 4 times 8, which is 32. So I'd have 32 whole 1/8 slices, and then I have an additional 3 1/8 slices. So this would be 4 times 8. Okay, if you want, you can draw out 4 whole pizzas, divide them into the 8 pieces, and color them each in, but it's 8 plus 8 plus 8 plus 8, which is 32, plus another 3. So when you're doing this multiply trick, it's because this tells you how many slices are in each of the whole number part. Therefore, the total will be 4 times 8, or 8 times 4. So that would be 32, plus the additional 3/8. So 32 plus 3 in this case would be 35/8. So is the improper fraction for this mixed number. Does that make sense? So now let's just write out the general form like we did in the flashcard, and now I think it'll make more sense. So A and B over C. So A, if we have a mixed number of this form, A is our whole number part, and let's say B and C satisfy the condition for a proper fraction, so B is strictly less than C. To convert this into an improper fraction, we do our shoop-doop pattern. So C times A, C times A, you take that product and then you add B. So multiply, add, in that order, right? So you multiply first and then you take that product and add B and then put the whole thing over C. So if I were to write that out, it's C times A plus B, and then you put that whole thing over C. Now usually you are introduced to this idea of mixed numbers and improper fractions more in the context of arithmetic, so you probably haven't learned algebra like at that point when you're first introduced to this idea, so this notation might not make as much sense. But for those of us who know algebra or are comfortable with it, this squishing C and A together in algebra just means multiply, right? So CA is multiplication. We tend to drop the times like this because it looks like X and you're working with letters and variables in algebra. So don't worry about that. Just write out the pattern if you want to focus on that. So here it would be multiply, but just remember that you are, when you say add over here or plus, right, that you are adding the total product. So C times A, you get your answer, your product, and then you add B. Okay, so it has to be in this order. But you do C times A, add B plus B, and then you put the whole thing over C. Now for those of us who are comfortable with our algebra, we can actually confirm this, right? So we built the intuition of saying each slice is going to be, each whole part is going to be broken up into C slices. So in total for A, we have C times A slices, or A times C, it's the same thing. We have A times C total slices for the whole number part, and that's how we got this. But if you want to check this algebraically, you have CA plus B over C. You can distribute this division over this addition, so you have CA over C plus B over C, which conceptually is what we did, but algebraically we can confirm. So the C's cancel and you get A plus B over C, which in this notation, the way we have it, is just A B over C. Okay, so it's all the same, math builds on itself, and usually you can confirm whatever you're doing before. But just a little side note there, so essentially we're always rewriting A as CA over C. That's all we're doing, and then adding our B over C, which then works out to be times add. Okay. Okay, so when we go the other way, it's essentially the same thing, but literally the other way. So let's go back to our 11/8. How do you go from an improper fraction to a mixed number? So now we just want to see how many whole pizzas, in this case, how many 1/8 slices or 8 1/8 slices can be pulled from 11 total slices. It's the other direction. So with fractions like this, it actually basically just means division, right? So 11 divided by 8. So when slices a remainder of 3. So I do 3/8 slices. It's the other way around. So you pull out however many whole multiples we can, which becomes our whole number part, and then we find the remainder here. So that's how we get 1 3/8. So I think we should just get some practice, and I think it'll just all make sense, yeah? So let's go from mixed numbers to improper fractions first. So let's say we have 1 3/5. Very similar to that first question, but let's just get into the pattern building now. So 1 3/5. So instead of 8 slices, our slices is going to be the same one whole pizza, but divided into 5 equal pieces, which I am not about to try and do, but divide that into 5 equal pieces and cut the slices that way. Okay, and so now we have one whole pizza, so that will be 5 1/5 pieces plus another 3. So 5 times 1 is 5 plus 3 is 8. 8/5. 8/5. Okay, so 5 times 1 is 5, and do that first, and then add 3, which is 8, and then put the whole thing over that original denominator. Okay, so let's do another one, and that's just to show you that this, is the same question. Before we had 1 3/8, but now we have 3/5, so that denominator tells us how many slices we are breaking this down to. But let's do another one. So like 3 6/7. Okay, here's our mixed number. 3 is the whole number, 6/7 is our proper fraction, 6 is less than 7. So I'll let you give this a try if you happen to be awake right now and wanting to practice. And while you're doing that, I'll just go ahead and write out a few other ones just for the sake of practice. And how about 2 3/4? How about that? Okay. So we're gonna do our 7 times 3 is 21. 21 plus 6 is 21 plus 6 is 27. Very good. So we have 27 sevenths. Okay, so 7 times 3 is 21 plus 6 is 27 sevenths. And the thing is, you can always go back and check your answers too, which is nice. So how about 5 and 1? 5 and 1/2. So 2 times 5 is 10. 10 plus 1 is 11. 11 halves. 11 over 2. Very good. 11 over 2. Good. So now 2 3/4. 4 times 2 is 8. 8 plus 3 is 11. Very good. So 11 fourths. 11 fourths. Already getting it. Very good. So like I said, the nice part is that you can go back and confirm your answers, because you can go from an improper fraction back to a mixed number. So you're basically doing 8 divided by 5. How many whole multiples of 5 do we have in 8? Well, 5 goes into 8 one whole time, right? So because if we have 2 5s, or 2 times 5, that's 10. That's too many, right? So 1 5, and then it leaves me 3 extra pieces. So 1 3/5. How many whole number of times does 7 go into 27? Well, 1 7 is 7. 2 times 7 is 14. 3 times 7 is 21. 27. So that's how we get the three whole sevens. But if I pull out 3 sevens, that's 21. So 27 minus 21 leaves me 6. So 6 sevens extra. So that's good. How many full multiples of 2 go into 11? That would be 5, because 5 twos is 10, but 6 twos is 12, which is too many. So we have 5 whole multiples of 2 that go into 11, and since that covers 10 of the 11, we have a remainder of 1, and so that's how we get 5 and 1/2. And there are 2 whole multiples of 4 that go into 11. 3 multiples of 4, 3 times 4 is 12, that's too many. So 2 for our whole 4s, which give us 8 pieces, and if we have 11 total, that would give us a remainder of 3, and 3 of the 4th, like 3/4, 3 of the 1/4 slices. Does that make sense? And so if we happen to have like 12 over 4, that just will be exactly 3, right? 12 divided by 4 is 3 with no remainder, so that won't be a mixed number, it'll just be a whole number. So this is just 3. Just because it doesn't necessarily have to be, but in this case they are all mixed numbers. Okay, so let's do a couple in the other direction just to get some practice in, and I think we're good to go. So 9 sevenths, and let's do 35 fourths. Okay, so let's convert these into mixed numbers here. So 9 sevenths. So how many full multiples of 7 go into 9? 9 divided by 7. We have 1 whole thing because 2 sevenths would be 14, which is too many. So if I have 7 sevenths is 1, then I have a remainder of 2 left. So 1 and 2 sevenths. And you can check again. Times plus. So 7 times 1 is 7 plus 2 is 9. 9 sevenths. Very good. And then how many 4s go into 35? Well, you can kind of try out some multiples here. I know that 9 times 4 is 36, which is too many. 8 times 4 is 32. So I will have 8 total. And then if 4 8s or 8 4s is 32, I have a remainder of 3. So 3 extra 1/4 slices. Okay, so this is our 4 times 8 is 32. 32 plus 3 is 35, and then I put the whole thing over 4 again. So you can always check. I think this way is actually easier, but you can always check.